Hello everybody, welcome back. In today's video, I would like to cover differentials. Now, some of you might be a little bit confused because we had a video called Differentials back in single variable calculus or linear approximation in differentials. We're going to go through basically the same thing just for the multivariable case. This is something that's somewhat important, and it's just something that we want to get done so that we can learn how to solve more equations and do more multivariable calculus, and to learn some approximation tricks that might be important in the future. All right, let's get started with differentials. So the definition for differential multivariable differential is that dz equals partial z partial x dx plus partial z partial y dy. Okay, and this should make sense. If I index these, dz or d, whatever you like, is equal to the partial derivative of z with respect to the partial derivative of the ith variable times the differential of the ith variable. So that is the more than two variable case that you can figure out for yourself. Anyways, if I want to rewrite this in a more succinct way, that should be dz, by the way. Dz is equal to partial x ab times x minus a plus partial y ab y minus b. Okay? And again, that should be fairly straightforward. That we have that kind of formula that's very similar to the second order, Taylor series that we were looking at, or the first order Taylor series that we were kind of discussing in the beginning of the video last time, that we had last time. So, of course, I would also want to preface this by doing an interlude to the idea of a linear approximation such that f of xy is equal to f of ab plus this, right? So this is kind of the your error, if you will. This would be your error. That's my approximation point. That's my normal point, or the point I want to approximate. So at this point, I add a differential, and then I get my next point there. Why don't we try an example? I would like to try one with differentials. So I'd like us to find the volume, or the differential for the volume of the cone. Now we know the formula for the volume of the cone is v equals 1/3 pi r squared h. So now what we need to use is that formula. So if we remember, dz is equal to partial z partial xi dxi. So what we need to do is we need to take partial derivatives with respect to our both variables, r and h, because v is a function of r and h. So we will take derivatives with respect to r and with respect to h, and then we'll tack on these differentials at the end. So the differential volume should be equal to partial v partial r times dr plus partial v partial h times dh. So what we get is when we differentiate this with respect to the proper variable, we get 2/3 pi r h dr plus 1/3 pi r squared dh. Okay, so we've now determined the differential for the volume of a cone. Now, what you can do with this is you can, instead of having these be differentials, you could make them delta r or delta h, and then you could find your errors given some problem statement. All right, in the next video, I would like to introduce the multivariable chain rule. That's an important rule when you're dealing with intermediate variables. So we will cover that in the next video. Thanks for watching, and we'll see you next time.